Okay. Yes. So, hello, I'm Makoto Hamana, coming from Government University, Japan. So this talk is about rewrite rules in GHC. So GHC has a feature of user-defined rewrite rules for optimization. For example, this map rewrite rule translates nested two maps into the single map, which can be regarded as more efficient than the two maps. So GHC applies this kind of rewrite rules to core program in the simplification process of GHC compilation. So, and these rewrite rules has been proved to be very useful in many libraries whose efficiency often depends on rewrite rules. But there's no formal theory of rewrite rules so far. And moreover, no rewrite rule checker has been developed for more than 20 years since the initial proposal of rewrite rules in the GHC in Haskell workshop 2001. So in this work, I want to improve this situation. And this is actually about how to ensure correctness of rewrite rules using terminating theory by giving rule correctness theorem, which I show. And to rigorously prove this theorem, so we also need suitable rewriting schematics of Haskell. And to give this, so we give a calculus called System FRE, which is roughly extension of system F omega extended with rules and equations. And we also provide a prototype tool called ReCheck, implemented as a GHC plugin that accepts real Haskell program and checks rules on the core programs based on my theorem. So I'll show you this in this talk. So first, to identify the problem in current GHC's rewrite rules, so let's consider this simple program. So this involves one rewrite rule that translates, that rewrites an expression f of something to the integer 1. But in the program part, there's a function which always returns 0. So what is actually the output of this main? The answer is actually output 1 because that by enabling rewriting feature in GHC, so GHC firstly rewrites this part to 1 in the desugaring simplification process, so the output becomes 1. But this can be considered as wrong. So this rule is wrong because, in principle, rules should not change the original meaning of the program. So we want to address the correctness of this kind of problem in this talk. So, but actually, there are several levels of correctness of rules. So first, I'll show you 3 levels of correctness. The first is about termination. So this is the most basic property to ensure to avoid compilation failure. So in rewriting theory, this is known as formalized as strong normalization of rewrite rules, which means that any computation rewriting passes are finite. And the second is about well-definedness. So unlike function definition, rewrite rules may provide an ill-defined function. So for example, this is a legal descriptions of Haskell's rewrite rules, but so we cannot predict what is the output of this main, because in GHA there's no particular rewriting strategy is assumed for applying rewrite rules. So this may be 0, maybe 1, or maybe undefined. So rewrite should be well defined, meaning that in rewriting theoretic term, rules should be confluent and strong normalizing. So this also gives a unique normalization property. And the third is about meaning preservation. Rewrite rule is called meaning preserving with respect to a program P. So if instances of left and right side by ground substitution theta have the same value evaluated by the program P. So this means that given a rewrite rule, we can have an instance of rewrite step by substitution theta. Then in this case, both terms must have the same value. So this is meaning preservation. So in rewriting theoretic terms, this is often called inductive theorems. And among these three properties of correctness, the relationship is as follows: that the meaning preservation implies well-definedness, which also implies a termination. So in this talk, I define the meaning preservation as a correctness property of rewrite rules. And because this is the most strict notion of correctness. And also note that this also means that to prove meaning preservation, we also need well-definedness and termination. So both of these are also important to establish meaning preservation. So next, let's consider another example. So this is a well-known append function, and this involves one rewrite rule for associativity of append. So this is actually rewrite rule. But this is one of the typical use of rewrite rules coming from natural property of data type. And in this case, correctness of rule is nothing but to prove that this equation holds under the assumption of this program, considered as equational axioms. But in this case, logically, this is not a theorem of first-order equation logic. So what kind of equation hold is that actually ground instance, so all ground instances of this associativity holds under the assumption of program P. So these regarded as equational axioms. And usually, so this kind of associativity on list is proved by using structural induction. But formally, adding a structural induction rule to equation logic is known to be not complete. And so not only this reason, but anyway, so in this work, I choose another approach by not only relying introducing structural induction, but so we just use rewriting property to deduce correctness of rewrite rule. So we establish the rule correctness theorem. This says that given a total Haskell program P and rewrite rule, suppose that program P considers rewrite rules with the rewrite rule to be checked is local confluent and also strongly normalizing. Then this rule is correct with respect to the program P. How this is proved is that as follows. let theta be a grand substitution, and then we can have a actual rewrite step of this rewrite rule L to R. So in this case, so we try to calculate the normal form of both sides, both of this rewrite step by using a program P. So they must have the normal forms of both terms because we have assumed that this is strongly normalizing. But these two normal forms may be different. But so in this case, consider that this D and D dash is connected by this rewriting passes, meaning that these are convertible. And we have assumed that so this is locally confluent and strongly normalizing. So by Newman's lemma, this means that so this is confluent. So we can have, by confluence property, we can have a common result of D and D dash. And also by using the totality assumption of the programs, so D and D dash are not constructor terms. So we cannot, so these can't be written by further, so these must be the same. So this means that this rewrite rule is meaning preserving. So this is proved. So next I'll show you how to apply this rule to check the correctness property of associativity of append. So in this case, first we regard these programs, this program as a rewrite rule. And also rewrite rule is, again, just a rewrite rule. And then it's not difficult to show this rewrite system is strongly normalizing. Because this is basically just a structural recursion, and this just moves the parentheses from left to right. And also, we can show that local confluence by using so-called critical pair analysis. So critical pair means that a critical situation that may break a confluence. And the critical pairs can be enumerated computationally by just checking the left-hand side, checking the overlaps of the left-hand side by using unification. So in this case, we can enumerate this. So there are actually 3 critical pairs, and all of them are joinable. And so what this means that, for example, this first critical pair, this means that associativity and the first rule is overlapped because so this excess may be nil. So in this case, so this part can be rewritten by the first rule, but this time also can be rewritten by applying associativity, but this can be rewritten to this part. So this makes joinability. And all of them are joinable. Then in rewriting theorem, it's known that if all critical pairs are joinable, then we can conclude the local confluence. So both of these assumptions are satisfied. So we can conclude that associativity is correct by the theorem. And so this next example is about the map-map fusion. So in this case, in programs, there is a definition of map and composition. So in this, so again, we regard these rewrite rules. And rewrite is just rewrite rules. And in this case, strong normalization of this rewrite system is not so straightforward because there is a function argument. But by using a suitable reducibility argument, we can show that this is strongly normalizing. And also, again, we can show local confluence of this rewrite system by enumerating critical pairs and checking joinability of all of them. So in this case, again, there are 3 critical pairs, and all of them are successively joinable. So for example, in this case, this shows that there are situations that the overlapping between map fusion and fast map rule, because this excess may be nil. Then so this part can be rewritten by the first rule, but we can also apply the map fusion, but both becomes nil by the first rule. Then two conditions are satisfied, so we can conclude that the map rule is correct with respect to the program by my theorem. So, but to more precisely state this argument, so we also need a more formal semantics of GHC's rewrite rules. But currently, it seems that there's no formal semantics. I just found in the GHC user's guide, there's an informal semantics. It says that matching in the GHC rewrite rules is matching modulo alpha equivalence, alpha conversion, and eta expanded if necessary. And if more than one rule matches, then GHC will choose one arbitrary. So this means that this is almost the same as non-high order rewriting system, but in this case, this must be polymorphic. And also, which also means that polymorphic part should be considered to be a polymorphic lambda-caluclus. So we propose a new system FRE, with the extension of F omega with general high order rewriting system. And sorry. But so before stating the system FRE, so we need to review how GHC itself is formalized. So GHC is formalized as by using the system FC, which is roughly extension of system of omega with let and case expressions. And in GHC compilation, any source program is translated to core. So core is equivalent to system FC. Any program is translated to core. And actually, rewrite applies at the level of core, not to the level of source program. So we formulate that system FRE is an extension of system omega with rules and equation. And we don't use let and case expressions. So what actually this means that, for example, so this is a Haskell program involving rewrite rule. And in the compilations desugaring process of GHC, so this Haskell program is translated to this core binding, which is that the binding whose right part is usually a lambda expression involving case and sometimes red, like this. And the rewrite rules are just translated to rewrite rules on core expressions. Yes. But in system FRE, so we regard everything is translated to rewrite rules. So which means that we don't, instead of using case analysis, we use this pattern. We keep this kind of pattern matching definition of rewrite rule. And also, this red binding is also lifted to top level rewrite rule. And rewrite rules are just rewrite rule, but on core. So, so this means that in system FRE, everything is rewrite rule. So which also gives the rewriting semantics of Haskell program. So I think that this is a bit similar to the spirit of Bass calculus mentioned yesterday, Simon Bento-Jones, which also choose a rewriting system by considering everything is as rewritable. So this shares a spirit of, so our work was spirit of the Bass calculus. And so we have implemented a prototype tool based on System FRE, implemented the GHC core plugin, so placed here. So this actually, our tool is called ReCheck. ReCheck handles the core expression after destructuring of Haskell program. So this means that, so ReCheck consists of translator from core program to rewritable, and confluence checker, and strong normalization checker, and correctness checker by our rule correctness theorem. And so this means that, so to obtain this rewrite rules, the actual process is not to translate from directly the source to this. So we actually translate this type of core program to the rewrite rules. So translate the this kind of translation. And confluence checker is based on critical pair analysis, but in this case higher order. So we need to we implemented the polymorphic higher unification to check create critical pairs. And strong normalization checker is based on a new criteria called polymorphic termination guarantee based on reducibility argument. And correctness is by our theorem. And note that so we have implemented so these techniques, actually simply typed version of these techniques in my previous tool called Sol, which participated recently international confluence competition and termination competition, and which actually won in both competition in recent years. So this means that so these techniques use the current state-of-art technology known in rewriting community. And yes, then so we have applied ReCheck to check the actual Haskell program. So many Haskell programs. I report several results. So, and as I have shown that append and map example, for this example, ReCheck automatically checks the correctness of the rules. And we can also consider the case of maybe a reader of some kind of monad with monad rows. In this case, monad row can be checked automatically correct with respect to monad implementation. And we can also prove the correctness of this kind of rule, and also show the strong normalization of some complex rewrite rule. So by these experiments, so theoretically ReCheck works well, but okay, but there are several actual technical issues in the implementation of ReCheck. So I actually, so one is that about module loading in GHC. So I don't know actually how to collect all relevant modules and the source codes or paths of used to the modules. So in practical, so I have tried to apply ReCheck to practical using program. So usually program depends on many other modules. But so we couldn't currently solve this issue, so we can't correct all relevant modules. So I should resolve this. And another is about the built-in functions. Built-in functions, so in this works, so as I should say, all program must be translated to reality rules. But built-in function doesn't have definition, so we cannot translate this to be reality rules. So this is problematic because to checking joinability of critical pair, we need to rewrite an open term, which may involve built-in functions. So we may need some partial evaluation or something like that. But I don't know how to combine partial evaluation and rewriting technique. And yeah, some more specific implementation is, I don't know. Actually, I'm not actually an implementer, so I haven't yet understood where the core is internal representation. So I must resolve. But actually, what I want to say here is that so I actually need help of someone. So I'm actually looking for collaborator, or postdoc, or maybe consultants, so to help to resolve this kind of issues. So if you know if you know some good idea to resolve this, so please tell me and ask me. Yeah, that's all. Thank you very much.
This is very impressive. There's a lot of way to walk between typical first order rewriting and System F omega. There's higher order polymorphism, etc. I'm not necessarily aware of the latest developments in rewriting theory, but so I don't know how much you've had to work, but what was the hardest in this? What caused problems technically?
So technically, so one technical issue is that at the levels of types, so high order rewriting is rather actually different from first order rewriting. First order rewriting is well established. But the higher rewriting is much difficult because of to calculate critical pair, we need a unification between rewrite rules. Right. But in the higher case, we need higher unification. And at the levels of polymorphism, we also need to take care of unification of polymorphic terms. So, but technically, these are not so very difficult. But usually, rewriting theorists are not interested in this kind of practical applications. For example, Haskell. But I try to correct relevant theoretical results. So, System F, rewriting, high order, unification, something, and then so I build a System FRE.
And what is the strategy? Do you try to eliminate higher order and polymorphism?
No, I don't eliminate. But,
so you play directly with it?
I need to extend suitably, theoretical soundly, the known results of rewriting at the level of higher order polymorphic case.
Okay, that's very impressive. Thank you.
Yeah, indeed, impressive. A quick question. The system requires the program itself to be already terminating to do something? Or what happens if I have non-terminating Haskell code and I want to pass it through your system? Will it be able to do something with it?
Could you say again?
So, sorry. if I understood the slide correct, then you need to prove strong normalization for program plus rules.
Yeah.
So what if the program itself already isn't strongly normalizing? Do you still get some useful signal from the plugin, or will it just not accept?
In this theorem, so we assume that the program must be strongly normalizing. So
Okay.
non-terminating program is not accepted. But we can also give so I forgot to say that I have also a draft paper on this subject. In that draft, I also show that we can also accept non-terminating program, which is not relevant to checking rewrite rules. So, but this itself assumes a strong normalization. But we can also refine this theorem that accepts that may involve non-terminating function in P, but which doesn't affect crucially to prove the correctness of the rule.
Okay, thanks.
Good. Any other questions? Okay, thank you very much.
Sorry. So finally, so I have uploaded a draft paper on this subject in my homepage. So if you are interested in, please look at. Thank you.
Good, thank you.